The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Most likely this will be a 2-hour lecture with a short break, so I'm teaching until 3 o'clock and we have the classroom until 3 o'clock. And let's jump right into cold fermions. Almost everything I say in this talk is summarized in a review paper which Professor Zwirlan and myself wrote a few years ago. The paper will be posted to the group website later this afternoon. Okay, when we cool down fermions, lithium-6, and boson sodiums, we immediately notice a difference. The sodium cloud shrinks and forms a small Bose-Einstein condensate, whereas the lithium cloud stops to shrink when we reach the degeneracy temperature. And of course, you know, it's at low temperature. At high temperature, the gases have very similar behavior, but at low temperature, they look very, very different. And that can be directly observed. We know that bosons do something very special at low temperature, and we talked a lot about it in this course. Namely, they become superfluid and form a Bose-Einstein condensate, whereas for single component fermions, there is some interesting physics. They form a Fermi sea, but nothing really special. So in order to do something more interesting with fermions, you need two kinds of fermions, and two kinds of fermions can form pairs. Just think for a moment, two atoms can form a molecule, and those bosonic pairs can condense into a Bose-Einstein condensate and become superfluid again. If that would be all to fermionic superfluidity, I would be almost done right now and would say, okay, a bosonic atom is a composite particle made of nuclei and nucleus and electrons. Well, a bosonic molecule is a composite particle, but in the end they do both the same. But the special things about fermions is there is another form of pairing which is much, much weaker, and this is the form which leads to superconductivity of electrons. It's Cooper pairing. And this is really much more subtle because the pairs are much larger than the interparticle separation. Now, in atomic physics, we have a wonderful tool to study pairing because atoms can form molecules, weakly bound molecules or tightly bound molecules, and we can control that in experiments with the Feschbar resonance. Assume you have two atoms which collide and they can form a molecule. And if you apply a magnetic field, the two free atoms and the molecule may have a different Zeeman shift, and therefore there may be a level crossing. And this is called, as a function of magnetic field, and this is called the Feschbar resonance. If the crossing is a crossing, nothing happens because the two configurations would not interact. So physics happens when there are interactions, through some hyperfine coupling, for instance, which takes the crossing into an anti-crossing. And now you see the following physics around this Feschbar resonance, that we have two atoms here. Here we have a stable molecule. Well, there are many, many more molecular states down there, but for this restricted Hilbert space, this is the lowest state. It's a stable molecule. The atoms, if you compare the solid line with the dashed line, attract each other because the solid line has lower energy, whereas on the other side of the Feschbar resonance, they repel each other. So therefore, if we look at the scattering length or the normalized force between atoms, we find this dispersive feature around the Feschbar resonance. And atomic physics wouldn't be the same without Feschbar resonances. We can now tune attractive, repulsive interactions. In a richer situation, there may also be zero crossings of the scattering lengths, which allows us to realize non-interacting systems and such. And Feschbar resonances were first observed at MIT some 15 years ago. So coming back to fermions, this Feschbar resonance gives us something very interesting regarding to pairing. On that side where we have stable molecules, well, those molecules are bosons, and those bosons form a Bose-Einstein condensate of bound pairs. Over here, we have attraction. But the attraction is not strong enough to form a bound state. At least two atoms in vacuum would not form a molecular state. The attraction is too weak. But we know from condensed matter physics textbook, if we have many fermions, if we have a Fermi C, then a Fermi C plus attraction equals BCS Cooper pairs. So now we have an opportunity by simply changing the magnetic field to go from real strongly bound pairs to weakly bound pairs and eventually to Cooper pairs, which would not form pairs in vacuum. And this is the kind of physics which was for the first time explored with ultra-cold atoms in the BEC-BCS crossover. Jenny?
Just to clarify, so in the repulsive regime, you say the atoms form molecules, but the atoms repel each other. So you're saying atoms that don't form molecules repel each other, or even when they're in this molecular?
Yeah, actually, if you look, if I go back to that, here they form molecules, here they repel each other. And actually, a lot of people think the repulsive side on the repulsive side of the Feshbach resonance means there is repulsion. But look, the atoms attract each other so much that they form a molecule. You can actually say the repulsion of the atoms comes because there is a very attractive molecular state below, and those two states repel each other. So the repulsion up here is actually caused by the molecular state down there. So in other words, if you go from the attractive to the repulsive side, many people use that, in terms of pairs, you go actually from very weak attraction, which is not sufficient to form a bound state, to stronger and stronger attraction, which now forms a stronger and more strongly bound molecule. Mark?
Other ways you can tell whether the molecule themselves are repulsive or attracted just by physics, or is it argument, or are you ready to look at calculation?
You mean what the force is between the molecules now? It turns out that the molecules are repulsive. In some picture here, when the molecule forms, you can say it's a loosely bound molecule, and the repulsion between atoms turns into repulsion of molecules. If you use the naive theory, which is, has approximations, you would actually find that the scattering length for molecules is exactly 2 times the scattering length for atoms. But if you work it out correctly, the factor is different than 2. Colin?
So you said that the molecules are bosons.
Yes?
I guess they're only bosons if the size of the molecule, like if the...
I come to that later.
Parts of it.
We come to that later, yes.
Well, my question was, I guess the size of the molecule scales pretty strongly with how far away you are from resonance.
Yes.
C6 or R6, balance or
in the universal regime, which is open channel dominated, sorry for talking shop, in that regime, the size of the molecule is equal to 1/2 of the scattering length. So as the scattering length diverges, the molecule is very, very big, and as we move away, the molecule gets smaller and smaller. But once we get out of this quadratic regime, out of the universal, the halo regime, then of course the molecular size is completely determined by the closed channel, and it is whatever it is in the closed channel, and there's no relation to the scattering length. Okay, so in other words, it is now possible, using Feshbach resonances, yes, I'm just missing colors, those dots should be red. Do we have a color problem? The red has turned into black, at least on the monitor. Red is much nicer. On the internal monitor it's red, it's just that the computer does not show red. Let me just try that. No, it's not cooperative. Just one more second. I have many more slides with color, so I just want to make sure that you recognize the features. Well, I don't see any easy fix. So So maybe we should live with just imagining some of the black is red. Okay, so in other words, by using a magnetic field, we can go from strongly bound pairs, which form a Bose-Einstein condensate, to weakly bound pairs, which resemble Cooper pairs of electrons in superconductors. So this is the physics of the BEC-BCS crossover, and in the middle of it, we find a new form of superfluidity, which has not really been realized before. Namely, you can say these are molecules which are too big to be called molecules, or these are Cooper pairs which are too small to be called Cooper pairs. It's really pairs which sort of elbow each other. They just fill all the space. The pairs are exactly as large as the spacing between atoms. Okay, you know, in class I always try to teach you something conceptual, and the conceptual part I want to address now is, let's assume we are on the right-hand side, on the attractive side of the Feshbach resonance. Two atoms weakly attract each other with a negative scattering length, but there is no bound molecular state. So how should you now understand that if you have many fermions, that those fermions form Cooper pairs and pairs? And the question I would have for you is, you've definitely probably heard about it, is this pairing mechanism which requires the Fermi sea, is that many-body pairing? That somehow correlation between many particles are necessary and it's a genuine many-body effect? Or can you still understand Cooper pairing as mainly a two-body effect? So in other words, how much many-body is really involved in creating pairs in the presence of a Fermi sea? Does anybody know the answer? What you hear from most people is that it's a real many-body effect. Two particles cannot form a pair in vacuum, so it is really many-body physics, and you say, wow, I really have to understand complicated physics. What? Pardon? It has something to do with the Fermi sea. What? Yeah, Timo first.
I may know the answer. Maybe you would like to.
Well, keep it away.
There is always a bound state in two dimensions, I think, with arbitrarily small attraction. And the Fermi sea helps you get to two dimensions.
That's correct. So what I want to show you is exactly what Timur said. You can really understand Cooper pairs. You can understand the exponential dependence on the scattering lengths by simply looking at one particle, at two particles with a very weak potential. But you have to look at it in two dimensions, and it is eventually the Fermi sea which provides the two-dimensional density of states. So in other words, the binding of Cooper pairs, at least qualitatively, can be understood with a single particle Schrödinger equation with undergraduate physics knowledge. Colin?
I guess the picture that was in sort of when you think of BCS in a real solid, like a three-dimensional solid, is that one electron traveling through the lattice repels all the electrons of similar spins, or Pauli exclusion. And then the electron of another spin moving with opposite momentum sort of sees that as a deficit of that spin component, sort of attracted to that region. So in that sense, isn't sort of this effective clearing out of other particles to make room for sort of another one, isn't that really a many-body associated with Fermi synthesis?
Very good. So we are talking about two different things here. One is we need an attraction. In the atomic system, we get an attraction because of van der Waals molecular forces. That's it. For electrons, which have Coulomb charge, where is the attraction? And you wonderfully described that there is attraction between electrons. It's like the couch effect. If you sit on a couch, you indent the couch, and the person next to you will move towards you. Similarly, when an electron goes through a lattice, it leaves a polarization of the lattice behind, and the next electron is attracted to this trajectory. So what you are explaining is the phonon-mediated process which leads to attraction. But if I have two fermions which attract each other, I don't need this complication.
But couldn't you even get it without like a lattice without fermions? I was just thinking like the Fermi gas, right? And one, if I have one fermion and I move it, sort of the location that it was has been sort of, all the other fermions have been pushed away from that location. So there's a sort of a density depletion there. So couldn't the other spin component see that as an effective attraction?
I mean, density depletion are density waves, and these are sound waves. Maybe there is a possibility to map it on phonons in a lattice. I haven't heard about it. So I've never heard about such an attraction which would happen in a Fermi gas, which would give the Coulomb repulsion through some correlation an attractive component. What is well described, of course, is the couch model or the phonon model you mentioned, but I'm saying this is just giving you the attraction. But the question is now, and that's the next question I raised, once we have an attraction between two particles, do we need many body physics or single particle physics to have pairing? So let me now address that. Now, this is out of the review paper. You can read much more about it, but it simply reminds you, undergraduate problem, what happens when you have two particles with a very weak attractive potential. And of course, since you can eliminate the center of mass motion, when I say two particles, it's the same as one particle attracted to a central potential. And what you learn, or what you may have already learned in your undergraduate days, is that in 1D, if you have an infinitesimal depth of the square well, you found a bound state. The bound state will decay very slowly, but it's a bound state. In 2 dimensions, you also find a bound state. And in 2 dimensions, logarithm appears. And often when logarithm appears, it's sort of the limit. The logarithm is the weakest form of binding. And if you go one step further, for a very, very small attractive potential, you do not have a bound state. So in 3 dimensions, you need a minimum, you need a critical energy of the square well, a critical depth before you have a bound state, whereas infinitesimal attraction is enough to bind particles in 1 or 2 dimensions. So therefore, when we talk about fermions with very weak attraction, in 1D and 2D, no problem, they can form pairs by that, pairs even in vacuum. But in 3D, we need something else, because an infinitesimal attraction is not enough to form a pair. Now let me ask you the following question. You all know that, let me just cover the slide because it gives the solution. You all know that in 3 dimensions, when you have radial symmetry, you can transform the 3-dimensional Schrödinger equation into an angular equation, but then also into a 1-dimensional equation for the radial wave function. And of course, this 1-dimensional radial equation has the same potential as the original 3-dimensional equations. So I don't know, I want to hear from one of you, why does now an infinitesimal square well potential with attraction give bound states in 1D, but not in 3D? Because in 3D, the radial wave equation uses the same infinitesimal potential as in 1D. Jenny?
Because you have to break down an effective potential that takes into account the centrifugal.
Perfect, but let's use L equals 0. Then the centrifugal potential is, the centrifugal correction is 0. Otherwise, you are right, it's an effective potential, but let's talk about L equals 0, S states, then there is no correction due to the centrifugal forces. Colin?
Radial derivative is no longer just a simple second derivative of sort of whatever.
No, it is. You have a more complicated radial derivative, but then you go to an equation which just says d2 dr square of a function u, and it's exactly the 1-dimensional Schrödinger equation, which you write down. You can transform the radial equation with a more complicated derivative into something which is exactly a 1D Schrödinger equation. Yes?
You can write an uncertainty relationship which won't be satisfied if the potential is less than.
Sure. Uncertainty relation always can immediately help you. You have an uncertainty relation for kinetic energy and you realize that you don't have enough potential. But maybe mathematically, what is different between the identically looking 1D Schrödinger equation and the radial Schrödinger equation for the wave function u.
I don't know how this is going to lead to it, but I noticed one difference is that in the three-dimensional case, you can't go less than 0.
Exactly. In the three-dimensional case, you have a wave function psi, but then you do a substitution that the 1D Schrödinger equation is not for psi, it is for u, and u is the radial part divided by r. So you transform to a different function which has 1 more power of r. And the requirement because of this is that your radial wave function of this one-dimensional radial equation has to have a node in the center. And now you see what happens. If you start at 0, your wave function shoots up. If you don't have enough attraction, it will never curve down and become a normalizable state. Whereas in 1D, you do not have the requirement that the wave function of your 1D Schrödinger equation has a node. So you have the same equation, the same infinitesimal potential, but the radial equation has a different boundary condition. So that's the difference. And that's important. It changes the physics completely. Okay, now it looks very different and it seems you have to, Nikki.
What about 2D?
Limiting case, we come to that in a second. In 2D, an infinitesimal potential is still enough. But now I want to show you how you can take care of all dimensions with one equation and not solve 3 different equations with 3 different, kinetic energy terms. And that goes as follows. You recognize that this is just Schrödinger's equation, kinetic energy minus energy equals potential. But now we can Fourier transform it. And the nice thing about Fourier transformation is that the second derivative is simply, spatial derivative is simply q squared. So therefore, if you describe now everything in Fourier space, you have q squared plus k squared times psi, but you divide by q squared plus k squared. Here you have a product. The product turns into convolution. Anyway, it may be not the most familiar way. You've seen it, but this is just Schrödinger's equation in Fourier components. And now we want to simplify that we have a short-range potential. So we assume we have a short-range potential. If you had a delta function, the momentum components of the potential would be constant for all r, but we get into something unphysical if you don't put in a cutoff. So we put in a cutoff. But with that cutoff, you can now rewrite the equation as follows. And now we want to do one thing. We want to integrate over q. Then on the right-hand side, we also have an integral over q. And then we divide by the common factor. And what we get is this. I know I'm going fast, but this is nothing else than rewriting Schrödinger's equation for you. But now look at it. It says it has an integral over all energies with the density of states, rho of E of energy. E is k squared. This is the energy of the bound state, and we want the bound state. And on the left-hand side, we have our infinitesimal potential. I mean, one thing is clear. If you have an infinitesimal potential, we can only get an infinitesimally bound state. So now we do the following. If the left-hand side goes to 0, the right-hand side if you go to an infinitesimal attraction, the left-hand side diverges. And the question is now, if the energy goes to 0, does the right-hand side diverge or not? In other words, if this integral where you said E equals 0 does not diverge, you cannot fulfill this equation with an infinitesimal attraction in the square-well potential. So therefore, the condition for bound state is now that this expression here with E equals 0 diverges. And this combines now all cases. And you have now an integral equation, and you can now solve it for infinitesimal V naught. V naught, you can solve it. What is the energy as a function of V naught? And in 2 dimensions, when the density of states versus energy is constant, you have the weakest divergence on the right-hand side. It's a logarithmic divergence. In 3 dimensions, this doesn't diverge. In 1 dimension, it diverges big time. 2 dimensions is the limit. There's a logarithmic divergence, and if you do the math, which is elementary, but I'm not doing it, you find that the energy of the bound state depends exponentially on -1 over the attraction. So for infinitesimal attraction, this turns to e to the minus infinity. It's the weakest bound state you can imagine, and this happens in 2D. Okay, let's go from one particle physics back to fermions. And let me now present to you how Leon Cooper really found the key ingredients to the long-standing problem, how do electrons pair in a superconductor? And he did the following. He made an artificial simplification, which you can say is ingenious. He assumed the following. He just wanted to understand how do 2 electrons pair, but he simply assumed that those 2 electrons are on top of a Fermi sea. So he pretty much said, I want to solve the problem where 2 electrons just scatter through all available states, and then figure out if an infinitesimal attraction between those electrons leads to binding. Of course, in a real world, the electrons in the Fermi sea are identical to those electrons, to those 2 special electrons, and they are constantly exchanged, but he simply made this artificial model. And then, of course, we can immediately write down the equivalent equation. It's exactly the same formalism, except for when we integrate over all energies here, we integrate, yes, we integrate over the 3-dimensional energy. But now we integrate only over a small region on top of the Fermi sea. And everything looks the same. We just have sometimes subtract the Fermi energy. All energies are now measured not relative to 0, but relative to the Fermi energy. If you compare it to the equation I just showed you for single particle bound state, you pretty much see that everything is the same, except for energies are measured relative to the Fermi energy. And secondly, we are not integrating from 0 as before, we start integrating from the Fermi energy. And that means now that in this area of integration, the 3-dimensional density of states is constant, namely it's the density for where the energy is the Fermi energy and can be pulled out of the integral. And then we have the same logarithmic divergence as we had in 2 dimensions. So therefore, the problem of 2 electrons scattering on the surface of the Fermi sea means that we have essentially the same condition for the electrons as if they would live in 2 dimensions. Question, if the world were 4-dimensional and we would have the same physics, we had 2 electrons on the surface of the Fermi sea, would the physics of the 2 electrons in that regard be 4 minus 1 dimension, 3 dimension, or would it be 2 dimensions?
How many dimensions is your Fermi sea?
Well, that's exactly the question. Let's assume we had 4 spatial dimensions. For this kind of analysis, is the effective density of states on the Fermi surface now 2-dimensional, or is it 3-dimensional?
Should be 3, right? It's kind of like you remove 1 dimension by restricting yourself to kind of the area of the Fermi sea.
It is the more, you know, if you say the particles have momentum on the Fermi surface, if the Fermi surface fixes 1 momentum, and now they have 3 different momenta. So in that sense, the motion on a surface in 4 dimensions is 3-dimensional. But it was sort of a trick question to some extent, because here we have reformulated everything with energy, and the question and the answer is now, the density of state is constant. It is the 4-dimensional density of states, but evaluated at the Fermi energy. So therefore, no matter in what dimensions you are, because you're restricted to the Fermi sea, you integrate over energy with a constant density of states, And if you pull the constant density state out of the integral, you have a logarithmic divergence and you pretty much get the same answer. So therefore, the physics in 4 dimensions would be the same. It would be the fermions which live on this Fermi surface would just marginally pair.
Then how do you explain the reduction of dimensions? Like where does one more dimension go since the things are still on the 3-dimensional surface in 4 dimensions?
Oh, well, the motion you can say on the Fermi surface is n-1 dimension. But the energetic analysis always uses a constant density of state, and the constant density of state is characteristic for 2 dimensions. So you have both. If you analyze the motion, yes, you have n-1 dimensions. But if you look at the question of bound states, you encounter the same situation as in 2 dimensions because the effective density of states is constant. Okay, so with that, the message I have for you is Cooper pairing is a single particle effect, a single particle trapped to an arbitrarily weak potential in 2 dimensions. And the only many-body physics which allows those Cooper pairs to form is that you have a Pauli blocking, that you have a Fermi sea which prevents particles from going into the deep Fermi sea. They stay on the surface and therefore they form weak pairs. So the only many-body physics which we need for that kind of pairing is Pauli blocking. Mark?
Sorry, can you explain again what is ER in the previous slide?
ER was the cutoff. We were cutting off the potential at the short. We didn't use a delta potential. We used a square well potential which extends out to R. And ER is the recoil energy associated with R. It's 1 over R squared with a few h bars and m to give it the units of energy. Colin?
If you go back to that, so I can imagine Taylor expanding my density of states in any dimension around Fermi energy. But I always have that constant term. The first term, so for 3D, it's e to 1/2. I'll have some linear term. Doesn't that imply that even if you give this the system any infinitesimal amount of energy, then that integral no longer diverges, and I get.
No, the question of divergence is robust. Depends only on the leading term and not on the expansion. If you have a divergence, you're not changing it by a small correction term. Because the small correction term is on top of unity. If you start with the density of states at 0, which goes with epsilon to some power, you have a different situation. But you catch really the physics by saying you take a constant density of states here. Anyway, let me just go on and say we should now figure out, and this is also important when it comes to pairing, which pairs are the most important one. And the message I want to give you here, the pairs which are most important one are the ones which have 0 momentum, because those pairs can scatter to all states on the Fermi surface without violating momentum conservation. However, if you have a total momentum of the 2 particles which is non-zero, they can only scatter on a segment of the sphere. And you got already the message that the higher the density of state, the better it is for the binding. So therefore, the pairs which have the largest binding energies will be the one with total momentum 0. Okay, now we go from Cooper to BCS. Those 3 guys figured out how they can now take the physics described by Cooper and really fold it into a correct many-body formalism. In other words, not to artificially have 2 fermions which scatter and there is just a Fermi sea of the other ones. They were now treating the 2 electrons which scatter on equal footing with the whole Fermi sea. So now we have democracy, all electrons are treated equal. So I want to derive for you the BCS wave function in the way which was not the way done by Bartin Cooper Schriever, but it makes an immediate analogy with Bose-Einstein condensation. So what happens is you could have now the idea, of course I'm very suggestive in leading you to this idea, two fermions form a pair. And if the pairs both condense, then each pair should be identical. So maybe we should take our n particles, our n fermions, n half spin up, n half spin down. Each of them should form a pair. So 1 and 2 forms a pair, 3 and 4 forms a pair, and such. And then we say our wave function of identical fermion pairs slash bosons is just the product of those pairs. But the pairing wave function, the molecular wave function, if you want, so phi is the same for all particles. So this is just like in a Bose-Einstein condensate, we have a product state of n times the same wave function. Here we have a product state of n over 2 times the same pairing wave function. Well, we should anti-symmetrize, that's important. So now let's just see what we got. Well, we describe everything in second quantization. We use field operators which create particles at a certain position, and then we have the wave function of the pairs to make sure they are created in the right position. We transform everything into operators, and we transform everything our operators, and we do Fourier transform. We go from operators in position space to operators in momentum space. But now it's just formalism. You can read up about it. But the important thing is now I define a pair creation operator. This pair creation operator creates one of those pairs. And what it does is it creates, we want to focus on the pairs with zero momentum. So it forms a plane wave, a fermion in a momentum state with minus k, with opposite spin with plus k. So these are sort of two opposite plane waves with zero momentum. But now the weighting factor is the Fourier transform of this pairing wave function. So if you have if you want to assume it's a molecular wave function, Fourier transform is, and this is the weighting factor. And with that definition, this is now the creation operator of, let's say, a molecule consisting of two fermions. Okay. So now we can say, well, maybe a good idea what describes our system is now, so to speak, a Bose-Einstein condensate where we create n over 2 pairs out of the vacuum. Well, first I want to show you that this is actually the BCS wave function. Most people do not use that form for the BCS wave function, but I want to show you that it's mathematically identical to the BCS wave function. But first I have to clarify, is that really a Bose condensate? If I would have shown you this equation without telling you anything about it, well, yeah, this looks exactly n over 2 identical B bosonic particles. But now we have to be more careful. We have our definition for the pairing operator. And now we can calculate, are those bosons? Let's just look at the commutator between B dagger, BB. Yes, fine, fine. But now the commutator between B and B dagger is not 1. It would be 1 if the probability that the population of one of those plane waves k, if that is much, much smaller than 1, then the commutator is fulfilled. But the population of momentum states depends on the size of the pair. If the size is huge, you have low-lying momentum states which have a huge population. If the size is small of the pair, you can say in a tightly bound system, particles have so much zero-point energy that every given momentum state has pretty much zero occupation. So in other words, this criterion here tells us that our pairs are bosons if nk is much smaller than 1, but if nk is not smaller than 1, then those pairs act out in a fermionic way. And the criterion happens exactly when the size of the pairs is comparable to the particle spacing. So in other words, what we have described with this wave function is we have a wave function which is a true Bose-Einstein condensate for tightly bound pairs. That's what we expect. It still has this form, but those pairs now feel the Fermi pressure. And therefore, we have this is automatically taken account in the formalism. Colin?
What's the minus sign? on the commutation?
This one.
Antisymmetry?
It's a commutator, not the anti-commutator. It's B dagger minus B dagger B. I just want to be careful here because for fermions you often use the anti-commutator, but I want to check whether these are bosons, so I use the bosonic, the commutator, not the anti-commutator. Let me just show you one thing real quick, namely that this wave function is identical to the famous BCS wave function. Well, almost, not quite. You know that this is a state which has n particles, n over 2 pairs. Remember when we talked about photons, we had Fock states with n particles, with n photons, but we also had coherent states where alpha square was n, but this was sort of a classical coherent state, and this coherent state could be expanded as a sum over Fock states. And one can now say to some extent, when it comes to certain properties of light, n photons, sometimes it's important to distinguish whether we have a Fock state or coherent state, but for many things, if you have n photons in the same state, you can have a laser, then you have a coherent state, or you have n photons in a cavity, and that may be similar. So let me now show you what happens when I take this Fock state, but construct what is now the coherent state version. In the coherent state version, I take, this here is a Fock state with J particles, but now I take a coherent superposition, and I've chosen my factor such that I will get a coherent state, and indeed, I get the coherent state. So this is the same, this is now sort of what the laser is for a Fock state is this coherent state for a state with a specific fermion number. And this state now, when I just, you can also say in many-body physics, we say, I just went from the canonical ensemble, which has a fixed number of atoms, to the grand canonical ensemble, where the number of atoms fluctuates. But now I can simply use the definitions. If I Taylor expand this component, because all higher powers of the fermionic creation annihilation operators give 0. The Taylor expansion ends after the first term, and with one more step, I have the famous BCS wave function. So therefore, the BCS wave function, which has been widely used to describe superconductors, is really identical to creating n over 2 pairs B, identical pairs B in the vacuum. And I'm just telling you that because that means now mathematically the BCS wave function, which many people say describes a very, very different physics, is formally equivalent to the wave function for Bose-Einstein condensate. Okay, so what have we done so far? We talked about one-particle physics, how very weak attraction leads to bound states. We realized that if fermions live on top of a Fermi sea, it gives at least the binding, the energetic consideration, a two-dimensional character, and we have two states, and we have bound states for infinitesimal attraction. And now we have used our intuition, if those pairs exist, if they form kind of a Bose-Einstein condensate, to construct a trial wave function. And now I want to take this trial wave function and show you how we can use it to solve the many-body Hamiltonian. So far, single particle physics, two-particle physics, intuition to get a trial wave function, but now we go to the many-body problem. Colin?
Yeah, a little bit. Can you go to the last slide? So the BCS wave function has like the normal component and the pair component. Where does the normal component come into the Bose?
This one? Or no?
Yeah.
Oh, we are talking here about t equals 0. We're talking about a wave function. We're not talking about finite temperature where you have a distribution over excited states.
Okay.
This is really zero temperature physics. I don't know, was that your question?
Yeah, that's kind of, yeah.
100% superfluid fraction. Okay, so We are back now, Timo.
Just before we get into this, this may be a silly question, but why is it that up has to pair with down? I mean, it seems okay for up to pair with up, right? You still have...
No, what happens is, we have assumed here that we have short-range interaction, and up can never come close together because of the Pauli exclusion principle.
But then in principle, if you have E wave or whatever attraction,
okay,
it could work.
You're talking about now, you know, different pairing mechanisms. I'm talking here about the plain vanilla BCS S-wave pairing, and that means spin up and spin down pair.
Okay.
Yeah. Also, this is where I can work out the analogy with BEC, BCS crossover and such. So I'm just giving you the simplest example. Yeah. But yes, in helium-3 at high magnetic field, you have one of the phases where up and up pair through P waves. It's a triplet superfluid. Okay, so we have the many-body Hamiltonian, and what I want you to sort of enjoy now is, I took you last class through the bosons, and you should maybe see how the fermions are different, but we use similar concepts. And so you may ask yourself at the end of the day, are the fermions really so different from the bosons when it comes to superfluidity? But we're getting there. Okay, so the standard assumption, let's make the same approximation. We use a delta function here. And we Fourier transform, we go from position space to momentum space. But now comes one important approximation. I mean, fermions are fairly complicated. Look, I mean, we have products of 4 operators, and we integrate over 3 momenta. Initial momenta, the initial momentum, the final momentum, and the momentum transfer. So we have an integral over 3 momenta. We have to do something. This is too complicated. And the BCS approximation is we only focus in the sum of pair operators that we scatter, or we have interact k prime minus k prime scatters into k minus k. So we pretty much say whenever we have in the interaction term 2 fermions, we are only looking at pairs where the center of mass momentum is 0. You can say it's an uncontrolled approximation, but it's based on intuition. So the hope is that we still capture the essence of superfluidity by doing this major simplification of the Hamiltonian. So now I want to show you that this Hamiltonian can be solved in 2 ways, and this really connects me with things you have learned previously. One is we can use as a variational ansatz this pair wave function which I just constructed. That's actually what Bardeen Cooper Schriefer did, but they used as a trial wave function the BCS wave function with the U's and V's, which is identical. But then I want to show you partially, because I feel nostalgic about the bosons, that you can also use the Bogoliubov transformation, the same method we learned for the bosons. So variational ansatz just means use this BCS wave function, which I just showed you, plug it into the Hamiltonian, and all you do is you vary the component, you vary the coefficients u and v until you find the minimum of the energy. And this gives you the famous BCS solution, and this is the plain vanilla formalism for superconductors and fermionic superfluidity. Okay, I don't have time to go into details, but I think you got the big picture. But let me now just emphasize the similarities we had with the bosons. We have a Hamiltonian, even with this BCS approximation that we got rid over one sum over momenta by focusing on the pairs with 0 center of mass momentum. We still have products of 4 operators. We want to get rid of it. But now we use a mean field idea. You know, we always get rid of products of 4 operators by grabbing 1 or 2 of them and saying we don't look at the operator, we look at the expectation value, which is the mean field. So we want to make a mean field approximation. Bogoliubov for bosons was simply we just took the operators C0, 0 momentum, and replaced them with the square root of n0, the number of atoms in the condensate. But now we have to be a little bit more subtle. So what we should now define is a pairing mean field. Not an expectation value of C0, but an expectation value of this creation or annihilation operators for pairs. It's a little bit more abstract, but it follows the same logic. So, and then we do the decoupling approximation, which I lectured about to you with the Mott insulator, that whenever we have products of operators, of products of pair operators now, we take the mean value, but we neglect the product of the fluctuations. Exactly what I've shown you before when we described the Mott insulator to superfluid transition. Okay, this is the pairing. This is the pairing field with an index k, and eventually it's important to define a delta, the famous gap in the BCS theory, which is the sum over all pairing fields with k. And it is this delta which plays the role of the condensate wave function exactly in the same way as psi, the macroscopic wave function in the Gross-Pitayevsky equation, played this role. So we do the same thing. We just kind of write it down. We drop quadratic terms, which are fluctuation terms. And the moment we have now simply a bilinear product of operators, we do exactly the same as we did with bosons. We transform to a new set of operators, which is the Bogoliubov transformation. Of course, this time we want to make sure that those we're transforming fermionic operators, so we want to make sure that after transformation we fulfill fermionic commutator, and then we determine coefficients in such a way that that cross terms cancel out, and what we obtain now is a diagonalized Hamiltonian. It's diagonalized, it has the ground state energy, and this you now realize, this is nothing like an harmonic oscillator. It's a quasi-particle gas of independent excitations. Gamma k is an excitation with energy Ek, and this means we've diagonalized the problem. I can't do justice to the formalism. I think the best I can do here for you is to show how the same ideas come back and solve the same problem. Also, everything is now for fermions. Mark?
Separate to like the delta times sum over k of the C operators, because here, yeah, here like in the very top line you have the sum k and k prime for this quadratic term, and then the next slide you have the delta, which is the sum over k of the expectation value, and then times the sum of k.
I derived it myself because it confused me, but I can just reassure you, if you take the original Hamiltonian, plug this into here, and neglect the product of the small fluctuations, you get exactly this equation. It's really just accounting and regrouping terms. There is no assumption, no concept involved. It's really just plugging it in. And the physics is that we neglect the correlation of the fluctuations. Okay. Yeah, I think I want to wrap up the fermions. We still want to talk a little bit about ions, but we have now solved it, either with a variational ansatz or with the Bogoliubov transformation. Two very different ways lead to the same solution. We have quasi-particles. Here, we determined what their energies are. Well, a little bit complicated equations to find what the quasi-particle energies are, but everything is known. We can now throw in temperature. Colin wanted final temperature. Well, what happens with this Hamiltonian final temperature? Well, we just have occupation number for those quasi-particles, the thermal occupation, and we have to self-consistency now look what happens in the presence of quasi-particles. This eventually leads to an equation for the critical temperature. So what we see here is as a function of the inverse scattering length, here we have a BEC temperature which is constant, and when we go on the BCS side where we no longer form bound molecules, we have this exponentially decaying temperature. For very small attraction, the transition temperature to the superfluid state is exponentially small. All this is theory, but it has been experimentally observed. If you want to pair fermions, we just need two states. At MIT, we use mainly lithium-6. Lithium-6 has many hyperfine states, but we just use the two lowest one in a high magnetic field where we have a Feshbach resonance. We pair the particles, well, we need a little bit lasers and equipment, and then we observe pair condensates. They look exactly like atomic condensates, but they're pairs inside. That they're really pairs inside, we found out with our F spectroscopy. And eventually, when we rotate the gases, we find vortices, and you know already vortices are the smoking gun of superfluidity. So with that, I've rushed you through an important and very elegant chapter of physics, the BEC-BCS crossover. Let me just sort of end with an outlook that I've talked about a basic phenomenon in bosons and fermions, both centered about superfluidity, because I think it was pedagogical to show you the differences and the similarities. But we can now regard those ultra-cold bosons and fermions as building block of quantum simulators, building blocks to understand in its simplest manifestation interesting physics. So you can say the Bose gases are quantum simulator for superfluid helium, the Fermi gases are a quantum simulator for superconductors. We briefly talked about optical lattices, which can be regarded as a quantum simulator for crystalline materials, but there is much more you can do with those building blocks.